All right, so for this step of the video, we're going to be deriving the Crank-Nicolson form of finite differencing for a heat diffusion equation, with the goal of demonstrating that this method of finite differencing does not have the same limitation as the previous one did, where R has to be less than 1/2. Crank-Nicolson. I'll grab a sip of water before we get started. So the first step in this derivation, similar to the previous one for finite differencing, is going to be writing out that heat diffusion equation. Yep, camera's on. Okay. We're going to write out our heat diffusion equation. So that's going to take the form of the first derivative of temperature with respect to time, d big T over d little t, is equal to alpha, which is that group of physical constants, times the second derivative of temperature, so d squared big T, over dx squared, so the second derivative of temperature with respect to position. I'm going to box it. This is our heat diffusion equation. Now, again, we're going to rewrite this in terms of finite differencing. So we're going to be using a form that takes the form of T sub j to the n, where j is our position index. Excuse me. So j represents a position in our medium, and n is our time index. So that represents a position in time, or a moment in time. And then also we are going to use the previous solution to our heat diffusion equation that we used in our previous finite differencing and stability analysis, where T is equal to e to the I, excuse me, I should say T sub n, or T sub j to the n is equal to e to the I k j delta x, and times e to the negative alpha k squared n delta t. Now, that doesn't matter right now, but we are going to incorporate that into our derivation in just a few moments. So we'll begin the same way that we did our previous finite differencing derivation, and we're going to split up this left side into a finite difference estimation of our first derivative. So it's going to be t sub j to the n plus 1 minus t sub j to the n all over delta t. So we're estimating the first derivative of temperature with respect to time, and that's why the n index is what's changing instead of the j index. So n for time and j for position. Actually, n plus 1, not n minus 1, excuse me. So n plus 1 minus n. We'll put parentheses around that. On the left side, we're going to have our alpha constant. Then I'm going to leave some space to put something under that. Actually, no, I will not. So on the right side, now instead of just doing a simple finite differencing estimation of our second derivative, which we did in our previous finite differencing example, the Crank-Nicolson method has us do it twice, actually. So we do the second derivative at n, and then we also do the second derivative at n plus 1. So in this case, we're going to be varying time and position. We're going to estimate the second derivative of temperature with respect to position twice at two different moments in time. We're going to take the average of those. We're just going to divide by 2. So that's where that 2 is going to come from. So I'll go ahead and write that out. So on top, we'll start with n plus 1, that's second moment in time first. So we're going to have t sub j plus 1 to the n plus 1 minus 2 t sub j to the n plus 1 plus t sub j minus 1 to the n plus 1. Now, again, this is our first estimation of the second derivative, and our j is going from j plus 1 to j minus 1. That's our position, and our n plus 1 is staying the same because this is all at one instance in time. Time would be equal to n plus 1. We're going to do it again for time is equal to n. So that's going to be, this is going to look similar to what we had in our previous derivation. So t sub j plus n, or j plus 1 to the n, minus 2 t sub j to the n plus t sub j minus 1 to the n. So we're going to divide that by our delta x squared, because we're taking the second derivative, or estimating the second derivative. We're also going to put a 2 in there, because again, with the Crank-Nicolson method, we're estimating the second derivative twice and then taking the average of those two estimations. That's why that 2 is in there. So we'll go ahead and rewrite this. So on the left, we're going to have t sub j to the n plus 1, just doing some rearranging here, is equal to t sub j to the n plus alpha times delta t, our time increment, divided by 2 delta x squared. Now this whole group of constants here, we're going to call that R. And again, this Crank-Nicolson method is seeking to demonstrate that we don't have the same limitation on this R value as we did in our previous derivation. So with all of these things pulled out, I'm just going to rewrite this group here, all of these T, J, N notation values here. So I'll go ahead and write those inside these, as a parentheses, I'll make those brackets. So we're going to write that inside these brackets. So we're going to have t sub j plus 1 to the n plus 1 minus 2 t sub j to the n plus 1 plus 2, or excuse me, just plus 1, plus 1 rather, t sub j minus 1 to the n plus 1. And we'll do it all again for n instead of n plus 1. So we're going to do plus t sub j plus 1 to the n, excuse me, minus 2 t sub j to the n plus t sub j minus 1 to the n. It's a little bit of a mouthful. I got to make sure I've got all our j's and n's in the right spot with the correct numbers. But from here, again, we're going to combine all of these constants into one r value. And now we're going to rearrange this one more time with all of our n plus 1s on the left, all of our n's on the right. And we're going to use all of these constants together as r. So I'll go ahead and step through that. So on the left, we're going to start with our j plus 1 to the n plus 1. So we're going to have a negative r, because we're on the left side of r equals fine, negative r t sub j plus 1 to the n plus 1. We're going to do a plus t sub j to the n plus 1. And we already had one over here, and we also have a minus 2 here. And since it's going to be minus here, it's going to be plus over here. So we're just going to pull out that t sub j to the n plus 1 and do a 1 plus 2r. And then lastly, we're going to have our t sub j minus 1 to the n plus 1 minus r because it's on the left. So we're going to do minus r t sub j to the n plus 1, and that's j minus 1, excuse me. So that's on our left side, all of our n plus 1 terms. We're going to do the same thing on the right side for all of our n terms. It's going to look pretty similar. We're going to have our r t j plus 1 to the n, and then we're going to do a plus tj to the n. Again, we already have one over here, and we've got a minus 2, so we're going to do 1 minus 2r. And then we're going to add, excuse me, we're going to add our final term where we have r tj minus 1 to the n. So again, we're just kind of working through, we are taking all of these constants as r, and we're doing some rearranging. So from here, we've got all of our n plus 1 terms on the left, all of our n terms on the right. So from here, we could do some further simplifications, and that's where this is going to come into play. And actually, before we do that, we're going to factor out all of these. So from each side, we're going to factor out the t sub j term. So on the left, we're going to factor out our t sub j to the n plus 1. And on the right side, we're going to factor out t sub j to the n. Now with those remainders, instead of leaving them like this, we're going to take those remainders and write them in terms of this E notation here, our solution to our heat diffusion equation, just like we did in our previous heat diffusion equation finite differencing model. So we're going to do kind of the same thing. And we're just going to factor out those t sub j terms. So starting on the left, we're going to factor out t sub j to the n plus 1. And then inside these brackets, we're going to have a negative r. Now, our j index is going to be stepping up 1 because we're taking out j. So we're going to plug 1 in for j here. That's going to be e to the negative, excuse me, just regular e to the I k delta x. That 1 plus 2r is going to stay the same, so plus 1 plus 2r. Then we're going to do that one more time, minus r e to the negative I k delta x. And this is negative because our j index, our position index, is stepping downwards. So that's going to be on the left. We're going to do just the exact same thing on the right. So we're going to have t sub j to the n being pulled out as a factor. And then inside, we're going to have positive r e to the I k delta x, again, using our solution to our heat diffusion equation that we proved was correct in the previous video, or an accurate solution to our heat diffusion equation. We're going to leave that 1 plus 1 minus 2r in there as well. And then we're going to have one more plus r e to the negative I k delta x. Now, again, just like our previous derivation, we're going to take advantage of Euler's formulas to do some further simplifications on this. So this formula is going to look like this. So Euler's formula states that e to the ix is equal to cosine of x plus I sine x, and e to the negative ix is equal to cosine of x minus I sine of x. So if we use this formula and then we go ahead and do some rearranging and some more algebra, we can go ahead and simplify this whole expression. So on the left, we will simply have T sub j to the n plus 1, which again represents the temperature at some position j at some moment in time n plus 1. And on the right, so all of that's on the left, and on the right we're going to have just T j to the n, which again is just our temperature at some position j and some time n, and then times a large factor. So on the right, all of this using Euler's formula is going to simplify down to 1 minus 2r, and inside of parentheses we're going to have 1 minus cosine of k delta x, close parenthesis, division, and then we're going to do this factor is going to be on the bottom. So again, if we follow that same simplification, we're going to have 1 minus 2r, 1 plus 2r on the bottom, 1 minus cosine k delta x, close, and then we'll close our brackets. I'll put a box around this. This is our final step. So from here, we have simplified our finite differencing using the Crank-Nicolson method instead of the previous method that we used earlier for our previous model in collaboratory that had that limitation. So to prove that this one doesn't, to demonstrate, not to prove, to demonstrate that this doesn't have the same limitation as our previous model did, we're going to do that same not sensitivity analysis, but stability analysis. So first step, we're going to be looking at this cosine term here. So cosine of k delta x. So we know that any cosine function is bounded by -1 to 1. Those are the bounds on any cosine function. Now, if we're going to take 1 minus that, we know that that whole expression, so this whole thing here, erase this line, this whole expression here, so we're taking 1 minus that, is going to be bounded by 0 and 2. So we know that this, this whole expression must be some positive value at any k and at any x. So this whole thing has to be positive between 0 and 2. Now we're going to be multiplying that by 2r. And we also know that 2r is always going to be a positive value. So again, r is alpha delta t over 2 delta x squared. Alpha, those physical constants, are always going to be positive. Delta t, our time increment, and delta x, our position increment, our space increment, distance increment for our model. Those are always going to be positive values as well. So we know that this expression, which is bounded by 0 and 2, times another positive value has to be some positive value as well. So we'll go ahead and rewrite this up here. And I'm going to call this whole thing that must be positive m, just an arbitrary variable for this demonstration. So we can rewrite this as t sub j to the n plus 1 is equal to t sub j to the n times the quantity 1 minus m over 1 plus m, where m is a positive such that m is greater than 0. M is some positive number. Now, if you evaluate this term here, 1 minus m over 1 plus m, we also know that this is bounded by -1 and 1. It always has to be less than 1. So that is the opposite case from our previous finite differencing derivation. So we know that there will be no compounding and that tj to the n plus 1 will always be less than tj to the n. So it's not going to approach infinity. Our model will not get crazy spikes when r is greater than 0.5. We know that this Crank-Nicolson finite differencing model does not have that same limitation, which will allow us to have much more reasonable values of delta t, our time interval, and delta x, our distance interval in our model. So again, this is the Crank-Nicolson method of finite differencing. Thank you. So in our previous video, we looked at how the Crank-Nicolson finite differencing method will allow us to eliminate any limitation on R for our Python simulation. Now, we're going to write out that equation in just a minute, but it would be very difficult to calculate by hand. Lots of unknowns, we'd need lots of equations, and it would be very tedious. So in our simulation, the computer or Python code is going to be applying matrices to our Crank-Nicolson format of that finite differencing equation. So we're just going to take a minute and walk through what those matrices look like. So again, for the first step, I'm going to rewrite that Crank-Nicolson finite differencing equation. Excuse me. So we're going to start out with a -r times t sub j plus 1, j plus n, j plus 1 to the n plus 1. On the left side, it's going to be all of our n plus 1 terms, as we saw in the last video. We're going to add t sub j to the n plus 1 times 1 plus 2r. And we're going to subtract another r times t sub j minus 1 to the n plus 1. Again, these are all of our n plus 1 terms. Right side of our equation is going to look very similar. We're going to start out with an r times t sub j plus 1. I always write j plus n. I mean j plus 1 to the n plus t sub j to the n times 1 minus 2r in this case. A few of those signs are going to be flipped as well. Plus r times t sub j minus 1 to the n as well. And I'll put a box around this. This is our Crank-Nicolson finite differencing equation for our heat diffusion equation in the x direction. So again, this would be very, very challenging to draw up by hand. So we're going to walk through how the computer is going to evaluate this. Excuse me, how the computer is going to evaluate this equation using matrices. So for this example, let's assume that we have a bar that we're going to split up into 6 segments. Now you could select any number of segments that you wanted to, but for this demonstration, we're just going to select 6. Now, instead of numbering them 1 through 6, we're going to number these 0 through 5 because those are the indexing values that Python will use for our simulation. So we're going to go 0, 1, 2, 3, 4, 5. Now, again, these are numbering our sections of our bar, our finite number of sections, in this case 6. So these will be all of our j values. Now, our problem states that the leftmost position and the rightmost position are being held at a specific temperature, or there's a specific T infinity being applied to those positions. So on the left, in this problem specifically, T sub 0, so T sub j when j is 0, is going to be equal to 350 Kelvin. And T sub 5, this rightmost position, the 6th spot, but the number 5 position when j equals 5, is going to be 400 Kelvin. Now, these are kind of like our boundary conditions or our starting conditions for a physics problem, but these are the values that are going to be held constant. Now, as you notice, there are 4 sections in the middle of our bar that have unknown temperatures, and that is the temperature profile that our model is attempting to determine, to model. So the first matrix that we're going to set up, we're going to split up this equation into a 4x4 times a 4x1 is equal to another 4x1. So we will set up that matrix over here. Now I'm going to begin by numbering our j values down our left side. So we're going to have j equals 0, j equals 1, j equals 2. Have to plan out our space on the board accordingly. J equals 3, and then 4, and finally j equals 5. So I'll draw our matrix with these values in the middle. J equals 1, 2, 3, and 4, because those are our 4 unknown sections in the middle of our bar. So we've got a 4x4 matrix right here. And then we're going to multiply this by a 4x1 matrix. And this is going to represent our T sub j at sometime n plus 1, because we're working on the left side of our equation here with these matrices. And I give myself a little bit more room there. So outside of this 4x1 matrix, we already know our T sub 0 and our T sub 5, which are going to be 350 and 400 Kelvin respectively. So I'll go ahead and add those in outside of that 4x1 matrix. So T sub 5 at n plus 1, anytime n plus 1, to go 400 Kelvin. And T sub 0, anytime n plus 1, is going to be 350 Kelvin. Again, because these are the boundary conditions that are given to us in our problem. Now, those remaining 4 values in the middle, those are the unknown values. So I'm going to go ahead and write those in. So we've got T equals T sub j, and j equals 1, n plus 1, T sub 2, n plus 1, T sub 3, n plus 1, and T sub 4, n plus 1. Now, this other 4x4 matrix, these are going to make up the coefficients that are on all of these temperatures on the left side of our equation for some instance in time where T, excuse me, where time is represented by the index n plus 1. So we'll begin with this term in the middle where we have just T sub j. So that means that any point, any j value, 1 through 4, all of those values are going to have the coefficient 1 plus 2r. So we can go ahead and draw those in, and it's going to form a diagonal line. And our other coefficients will as well, and we'll see that. But this is going to form a special kind of matrix called a diagonal matrix that Python is going to evaluate in this way. So we'll start out with 1 plus 2r, we'll carry that down in the diagonal and apply it to all of our j values. So again, this forms a diagonal line because all of our j values, 1, 2, 3, and 4, are going to have that coefficient on them as well. Looking one term over, we also see a negative r coefficient on that temperature. But this starts at j plus 1, not j. So in this line here, we've got j equals 1, so that's going to be T sub 2. So we're going to move one line down to write that negative r. There we go, forming another diagonal line parallel with the first. And then these values are all going to be zeros. I'll draw a line just to symbolize that those are separate. And then anything outside of this line is going to be a 0. Looking at our last term on the left here, we also see another negative r coefficient, but at j minus 1, position j minus 1 instead of j plus 1. So that's going to be another diagonal line of negative r coefficients just down like that. And then zeros in those other positions, of course. Now, that looks a little bit messy. These are supposed to be in the same line as we go down, but I think I'll move that up so it's a little bit more clear. There we go. So again, these are our diagonal lines that make this a diagonal 4x4 matrix. Now over here on the right, we're going to have another 4x1 matrix where we are simply going to write out this side of our finite differencing equation using the Crank-Nicolson method, subbing in each value of j, so 1, 2, 3, and 4 inside of our matrix. So starting with the first term, we've got r times t sub j plus 1 to the n, so we're just going to start with that. We've got r times t sub 2 to the n, because in this line j equals 1, so the spot here, plus 1 is going to be equal to 2. So I'll carry that down for all 4 of these j values. So we've got r times t sub 3 to the n, r times t sub 4 to the n, r times t sub 5 to the n as well. Returning to this first line where j equals 1, we're going to add t sub j to the n times 1 minus 2r. So for this, we're going to just add simply 1 plus t sub 1 to the n, 1 minus 2r, because again, in this line, we're just dealing with j, and j is equal to 1. So if we carry that down for all these other rows, t sub 2 to the n, t sub 3 to the n, and t sub 4 to the n for the bottom line, all multiplied by that same value in parentheses, 1 minus 2r. 1 minus 2r. And lastly, we've got one more factor listed here, or one more term listed here, which is going to be r times t sub j minus 1. Excuse me. Raised to the n power. So we're going to have r times t sub 0 in this case, because we've got j equals 1. 1 minus 1 is 0 to the n. We'll do that for all of these. So t sub 1 to the n plus r, t sub 2 to the n, and plus r, t sub 3 to the n. So at this point, we've gotten all of our terms done, but we're not quite finished yet. We've still got 2 more. There's going to be one here and one here in our first and last lines that we can close out this matrix over here. Now, the reason that we still have 2 more is because if we look over here in our top and bottom lines, we still are missing one of those negative r coefficients. And again, these represent the temperatures at the end of our bars, and we do, in fact, need to account for those in our matrix because those are important values. Those are going to ultimately determine how that temperature profile works, what it looks like when it's done, once it reaches a stable profile, where that is located on our graph of temperature in our model. So for our top line, we are missing this 350 Kelvin value, and that negative r coefficient is missing here. So we're going to add. We're going to bring it over to this side, get rid of the negative, so we're going to have plus r t of 0. Now, similarly over here, we're also missing that j plus 1 value. So we're going to bring that over here, same as we did up top, plus r t sub 5. So at this point, we've pretty much outlined what the matrix setup is going to look like in our Python code and how the Crank-Nicolson model, or excuse me, how our collaboratory Python model is going to evaluate the Crank-Nicolson equation for finite differencing to model that temperature profile of our bar. Now, the temperatures are going to be the same. There will be quite a few more segments in our bar, but again, this is just a simple demonstration of how these matrices come about. And this will allow the computer to solve it in a much more efficient way than if you or I could by hand. So, and then we'll hop on over to collaboratory next. Thank you. All right, so here we are in the last section of our video. And in this portion, we're going to be hopping back into Collaboratory to modify our Python simulation to include the Crank-Nicolson version of the finite differencing heat diffusion equation in order to model our problem. And as a reminder, our problem is going to be, excuse me, to simulate the temperature profile of a bar that is uniformly heated to, or that is uniformly 300 degrees Kelvin. And then at the left side, it's going to be heated to 350. And then at the right side, it's going to be heated to 400. So again, our simulation is going to be to model the temperature profile of that bar as that heating develops over time. So here we are back in co-laboratory, and if you recall from the previous section of our video where we looked at this code, this is a Python model of our simple finite differencing model of the heat diffusion equation. Now, we could create a really nice graph here where we can see these temperature profiles evolving over time. However, this model had a pretty significant drawback. If R is increased to over one half, and we go to simulate, all right, I forgot to run this first one. So again, if we increase R to over one half and we go to simulate these temperature profiles, our graph gets really weird and we get a very unreliable and unstable model because we get temperatures in a very, very, very high order of magnitude. So I'll go ahead and put this back to 5 because that is the upper limit. That is the upper limit of the R value for our simple finite differencing model. So I'll go ahead and run that again so we get our nice graph back. There we go, nice and linear, very good. And for the Crank-Nicolson finite differencing model, we're going to be modifying this code in order to incorporate the Crank-Nicolson method, which will allow us to eliminate that limit of 1/2 for the R value. So the first thing that we're going to do to modify this code is going to be import another tool for us. So we're going to do from scipy dot linear algebra import solve banded. So if you recall in the previous derivation, the one video ago just talking about the Crank-Nicolson formula, I referred to one of the matrices that we form as a diagonal matrix. While technically it does form a diagonal pattern, this is actually going to be called a banded matrix, which makes sense because the tool that we're going to use in Python is called solve banded. So again, that was just a small error on my part. That's actually called a banded matrix. So again, this first block here, just like it was in the previous code, just bringing in some tools for us to use. And for this one, we're going to add the solve banded tool from the scipy linear algebra library. So for the next step, we're going to come down here come down after our first graph from the regular finite differencing model. We're going to go ahead and repeat some of those same steps. So first, we're going to set up our array of temperatures. So we're going to go np.full. And then we're going to have nx, which is the number of discretizations of our width. So the number of chunks, which in this case is going to be 100. And they're all going to start at 300 Kelvin. Now from here, we're going to go ahead and define the left side at T0 as 350 Kelvin. And we're going to define our right side, so T-1, as 400 Kelvin. Now, again, just like we did in the previous code, T0, that's going to be our first value because our indexing starts at 0 in Python. And then T-1 is going to represent the final value in our array, just because it's going like one step behind the first one, which would be the last. So it rotates around. So T-1 is going to be our last value. So just repeating some of the steps from our first model. Now from here, we are going to set up two different matrices. So the way that the solve banded system works, or the solve banded command in Python works, is that it's going to deal with two different arrays, A and B. So we're going to start with A. We're going to go A is equal to np dot zeros, and then we're going to have a 3 by nx minus 2 array. Or matrix, that is. So this matrix is going to be made up of those 3 different bands that we saw in our 4x4 matrix. In the example that we did in the derivation, the 4x4 matrix that was on the left, in this case, it's going to be quite a bit larger, but that matrix had 3 diagonal bands in it. The one was 1 plus 2r, and the other 2 were negative r. So we're just going to go ahead and define those in our new matrix A. So we're going to have 0 onward in our matrix is going to be negative r. Negative r. And we're going to have 1 onward is going to be equal to 1 plus 2r. And again, these are just 2 times r. 1 plus 2 times r. And again, these are just the bands that occur in that matrix as we write it out. And then we will finish with another negative R. Oops, got fat fingers today on the keyboard. It's not going so well. Negative R. Okay, so that's going to be the first matrix that we're going to deal with our solve banded program in Python. So the second matrix is going to be B. So we're going to do a kind of a similar thing here. We're going to say B is equal to np.zeros. This one is just simply going to be nx minus 2. So this is a one-dimensional array or one-dimensional matrix or vector or simply an array with width nx minus 2, which in this case is going to be 98. Now these are, because we know the first and the 100th spot on our bar, which are going to be those set temperatures of 350 and 400 Kelvin respectively, this array, or both arrays actually, A and B, only need to be nx minus 2, or in this case 98 units long, because we do know those first and final sections. So now we're going to define B, and this is going to come straight from our Crank-Nicolson equation in the previous video where we derived that equation for the heat diffusion equation. So we're going to have R times T sub j to the minus, or excuse me, T sub j minus 1. So again, if we recall, T sub j is just going to be 1 colon minus 1. So if we subtract that, we're going to have 0 colon minus 2, or simply colon minus 2 in our Python syntax. And we're going to add that to our T sub j term, which is going to be T to the 1 colon minus 1, or T times 1 colon minus 1. That is going to be multiplied by 1 minus 2 times R. 1 minus 2 times R. And we're going to go ahead and add another R times, this one's going to be Tj plus 1. So we're going to have, again, 1 colon minus 1 is Tj. So if we add 1, that's going to be 2 colon 0. So, or, let's see, 1 minus 1. So it's going to be, 2 colon 0. We can just go 2 colon to take it to the rest of our, array, or excuse me, that word was totally escaping me. The rest of our array, the rest of our vector in this case, 2 colon 0. There we go. Alrighty. So from here, we're going to go ahead and define specific values of B in that array. So we're going to begin with B of 0, B0, and we're going to go ahead and add R times T0. This is because with the way that those matrices are set up, we exclude those first and final sections of our bar, so we do have to add those back in. So we're just taking B0 and adding R times T0. And then we're going to do the same for the last value in that B array. So we're going to have B minus 1 equal to B minus 1 plus T minus 1. In this case, that one is good. T minus 1 is going to be 400 Kelvin, and then T0 is going to be 350 Kelvin. All right. So from here we have our both our A and B arrays set up. All right. Now from here I'm going to run a little test just to make sure we can get our initial temperature profile. So I'm going to define a new figure. So I'm going to do fig2 equal to make subplots. And this is going to look very similar to our previous coding experiment, previous model. Make subplots, rows equal 1 and columns equal 1, just because we only need one graph, one by one column and one row. And then we're going to do, let's see, always miss those parentheses, it gets me every time. And then now we're going to do fig2.add underscore scatter. We're going to say x equals x, which is previously defined in the earlier parts of this model. Y equals t, mode equals lines, and name equals initial. Now just make sure we get all of our imports good. I'm going to go ahead back to the very beginning and run this all the way through just so we check all of our boxes. And again, this is just going to be a test to make sure that we can get that first temperature profile using the Crank-Nicolson method. So go back to the beginning, go from here. So now we will do shift enter, shift enter, shift enter. This will be the graph from our first model. We'll do shift enter, shift enter, shift enter, and shift enter. Awesome, very good. So as we can see here, the Crank-Nicolson method, now we only did it once just because we're only doing one temperature profile in this case, gives us our beginning temperature profile. We've got 300 Kelvin all the way across our bar, 350 on the left, and 400 on the right. So far, so good. Now the next step, we're just going to get rid of this, and I will get rid of this as well. That was just a little test. The next step is going to be to set up our for loop, just like we had in our previous example. So it's going to look very similar. So it could be for I in range 1 to nt plus 1. Nope. Nt plus 1. There we go. Colon. And now we are going to call that solve banded command that we imported from that library all the way at the beginning of our collaboratory page. So now we're going to do, let's see, we're going to have t sub 1 colon minus 1. So we're just defining the temperature at a specific point in space and time. And we're going to have solve banded. And the way this is going to work, we're going to have a 1 by 1, and then we're going to call an A and B, those two arrays. So that pretty much is it so far. And now we still are going to need our if I modular 100 is equal to 0, not 1, 0. Then we're going to add another, let's see, we're going to, yeah, I shouldn't have deleted that code because I still need to establish that, graph. I'll add that in just a minute. So we're going to do fig2 dot add scatter. We're going to do x equals x, y equals t, mode equals lines, and name equals. Now instead of calling this initial, we are going to go ahead and call this, we're going to do a formatted string, so f, and we're going to call this just our index I. Now again, this little string here, that if statement, is just to make sure that we're not graphing all 10,000 temperature profiles, but only graphing the multiples of 100. So we still get all those iterations, but it is only graphing a few of them, not all of them, just what makes it a heck of a lot easier to read. And then of course, our last step is going to be fig2 dot show open close. Now, again, I did delete that little code there, so I'm just going to go ahead and move. Can I scoot this up? I think I should be able to scoot that up. Perhaps not, but we can't do it here. All right. I'm going to scroll up and take a look just to see how we did it here. All right, yeah, that's going to be the exact same. So I'm just going to copy, paste this, and then I will modify that to. So we're just going to pop that in here. We're going to do fig2. It's going to be pretty much the same stuff. All right, make sure our loop looks good. Fig2 show. All right, we'll go from the very beginning one last time. Actually, I have to do it a few more times. But. All right, so here's from our first model, the standard finite differencing model, and we'll proceed with our Crank-Nicolson model. It should look exactly the same if we did everything right. All right, doesn't look the same. Let's see what we can do. Let's see what we've got here. Oh, I remember what it is. Gotcha. Yep. So inside of our for loop, we do have to re-establish our B as we go. So we're going to go ahead and copy this in, these 3 lines of code inside our for loop. I did miss that. We're going to put those down here. The for loop did seem a little bit small to me. It was like, oh, I think I'm missing some stuff here. All right, we're going to do tab. Now that should fix this problem. We're going to start from the very beginning again just to make sure, and we'll see what happens. Control Shift, or excuse me, Shift Enter, Shift Enter. Standard finite differencing graph. Shift Enter, Shift Enter, Shift Enter. Now, fingers crossed, Crank-Nicolson graph. That still doesn't look quite correct. Oh, definitely not correct. We're going all the way up to 600. Got to see what's going on here. Let's see, live troubleshooting, absolutely. All right, I'm going to try going from the very beginning one more time. There's a few occasions where that has fixed the problem, but I don't think that's going to be the case here. We'll just try it once to see. Oh, here we go. Let's see. So when we are doing our second, we're adding that t negative 1 term to b. Forgot to multiply that by r. It's one thing I noticed. Hopefully that'll fix our problem here. R times. Yep, so when we're adjusting our b minus 1, we're going to add r times t minus 1, not just t minus 1. That would make a lot of sense. And that's why this would be so high, because we're going to be adding 400 instead of adding 200. Yep, that would make a whole lot of sense, actually. So let's go ahead and start from the very beginning one more time and see if that fixes our issue here. All right, so standard finite differencing. Pretty standard. And let's see, Crank-Nicolson. There we go. That looks pretty good to me. So again, these are going to look pretty similar. So starting with the standard finite differencing that we had before, we've got our initial temperature profile down here, 300 all the way across, 400 on the right, and 350 on the left. And then ultimately that's going to form a line, straight line going in between when r is equal to 1/2. Now with our Crank-Nicolson format, our Crank-Nicolson method, it's going to look, again, pretty much identical. So we've got 350 to 400 on the left and right. And then on the bottom, we've got our bar going all the way across with our initial temperature profile at 300. So we can see how that temperature profile evolves over time. So basically, so far, we've just demonstrated that the Crank-Nicolson finite differencing can do the same as the other finite differencing that we've already done. But again, the whole reason why we're using the Crank-Nicolson method instead is because if we switch our R to above 1/2, now the example that we used previously was 0.55, we got a really funky graph with our previous model. So we'll start from the beginning with R above 1/2 with R equals 0.55 and see what we've got. So our standard finite differencing from from earlier in the video gives us a very funky graph, really high temperatures. So this is an unstable model. And if we proceed with the Crank-Nicolson, look at that, we still get a stable model. We've still got 300 all the way across the bottom for our initial temperature profile with the 350 and 400 on the ends. And then eventually over time, as we get through all of these iterations, we're still going to approach that line from 350 to 400. So that's terrific news. This is just demonstrating why the Crank-Nicolson is the superior method in this case. And the reason that the ceiling of 1/2 for R is such an issue with the previous model is because that's not a super realistic value for R. So R is equal to alpha times delta t over delta x squared. On the Crank-Nicolson model, it's 2 delta x squared on the bottom. But if we have a limit of 1/2 on our R value, that means that our delta t, so our difference in time, can't be too high. And likewise, our difference in position can't be too low, which means that we were limited with the resolution that we're able to get with this model. But as you can see, with the Crank-Nicolson model, we're able to still use R values that are higher than 1/2 and still get a reasonable model. So just to demonstrate that even further, we'll try a few more options for R. So we'll just go 0.81, again, just an arbitrary value, start from the beginning and step our way through. So the regular finite differencing, again, gives an unstable model. And then our Crank-Nicolson model gives a beautiful, stable banana model. It looks really, really great. And then finally, we'll do that with just one more time with R equals 1. See what we get. We'll step through it one more time. Still, we get unstable for the traditional model, or the regular finite differencing that we had done previously. And the Crank-Nicolson model still performs beautifully. We've got a realistic temperature profile stepping from the initial all the way to the final. We've got a line between 350 and 404 hour bar. Perfect. Well, thank you so much for watching. I know it was a little bit rocky there in the middle as I kind of troubleshooted that during the demonstration, but it looks like we found some success in proving that the Crank-Nicolson model does not have the limitation on R that the previous model did, and allows us to answer our problem, to solve the issue that we're dealing with of trying to model the temperature profiles of a bar at 300 Kelvin that is heated on the left with 350 and on the right with 400 Kelvin. And as you can see, we got a really nice model using the Crank-Nicolson technique there with, again, no limitations on R whatsoever. So there we go. Thank you so much.